Okay, folks, here's the next Mr. Bryant video lecture, this time on centripetal force. So here we're going back to an image that we looked at before, the image of the person swinging the yo-yo above their head. The only thing that keeps that yo-yo swinging above the person's head is a force that directs the yo-yo's motion constantly toward the center. Now, the yo-yo at any one moment in time is actually moving in a direction tangent to a radius drawn through the circle, as you can see on the diagram. The force that the person is exerting through a tension force through the string, however, it's constantly redirecting that yo-yo's motion toward the center. As with any acceleration, we don't get that acceleration without a force being exerted. If we want to find out what this force is, well, we have a couple of equations. The force that maintains centripetal motion is called a centripetal force, and it's measured in newtons just like every other force. We have two different formulas for that. The mass times the object's tangential velocity squared over its rotational radius, or its mass times the radius times its angular speed squared. The centripetal force, and this is an important point here, is not actually a force in and of itself. It is a force produced by other forces. Gravity and friction, electromagnetic forces, can all cause objects to move toward the center of rotation. So let's look at a fairly common and fun example of centripetal force. Roller coaster car going upside down. When you get in a roller coaster that goes upside down, you're always given a harness that holds you in. In reality, however, the centripetal forces that accelerate you toward the center of a loop as you go around, assuming they're large enough, would allow you to go through the ride completely unscathed without the use of the harness. The roller coaster, as soon as it moves around the loop, keeps going around that loop because of forces that accelerate it and all of its riders toward the center. As the ride is going up the loop, the force that keeps the riders going toward the center, and the entire cart for that matter, is the force of the roller coaster cars pushing against the track with a response force of the track pushing against the cars and the riders. After the car goes through the top point of the loop, the force that keeps the ride accelerating toward the center is mostly gravity. Let's take a more in-depth look at that in this diagram. If you look at the colored lines there, the brown lines represent the force of gravity on an object moving through a loop. The pink line represents a normal force, or response force, of the track pushing against whatever car is going around the loop. The blue colored line that you see represents the direction of the car's motion at any one point. As you can see at the bottom of the track, gravity is acting down away from the center of the loop, so it is not actually causing any centripetal force at this time. The only thing at the bottom of the loop that is causing the car to maintain circular motion would be the normal force. At the side of the loop, gravity again is pulling straight down and not exerting any centripetal forces. The only thing keeping the car in circular motion at that point is the normal force resulting from the seats pushing on the riders. At the top of the loop, we're going to have two different centripetal forces. Gravity, in this case, is acting toward the center of the loop, so it acts as a centripetal force. We also could have the normal force pushing downward as well, assuming that the people on the ride are going fast enough that they're pushing against their seats at the top of the loop. We can also have forces like friction accelerate objects as they go through a curve. If you look at the picture of the car on your left, The only reason it can turn is because there is a friction force exerted by the road on the car that accelerates it toward the center. Sort of strange to think about it, but the only reason this car, and in fact any car that you can drive, can turn at all is because of a friction force exerted by the road onto the car. In slippery situations, when the road is covered with ice, there is no friction force sufficient enough to cause cars to be able to turn, which is why, if you've ever had the joy of trying to turn in cold and nasty weather, your car just keeps going forward rather than turning. You can see this effect on the diagram on the right-hand side of the screen. On the left, we see the path and forces involved for an object that can successfully follow a circular path. There is a sufficient enough centripetal force to keep the object curving. Without that force, the object would simply keep traveling in a straight line. So imagine a car on a slippery road being like the first couple of green dots you see at the bottom of the screen, and then the white dots and the straight path above it. There's not enough centripetal force to keep the car moving in a circular path. All it will do is keep skidding forward. A rather unpleasant situation, and one that can make one move from the great Northwest to Baton Rouge, as the case may be for me. So, let's look at a situation where we have to calculate a force that causes centripetal motion. We have a 1,000-kilogram car driving around a curve that has a radius of 50 meters. The car has a velocity of 14 meters per second. So let's think about the type of velocity we have there. That's a tangential velocity. That's not an angular velocity or speed, because those measure the angle that we go through. The thing that's going to cause the car to move in a circular path will be static friction. It's a little unusual to think about, because normally we associate static friction with objects that aren't moving. But relative to the direction either in or out of the circle that the car is in, the car is actually at rest. If it maintains a constant radius as it turns, that means it's not getting any closer or further away from the center of its rotation. So it's static friction that actually keeps pushing the car in a circle. If I give you the coefficient of static friction here, which is 0.6, can you determine whether the car will follow a curved path? Attempt to work this problem yourselves, and then move on to the solution. So, first off, what we need to do is figure out what is the maximum force of static friction that will act on the car. The max force of static friction will be the coefficient of friction multiplied by the normal force on the car. The maximum force of static friction is 5,900 newtons. Therefore, what we need to do is take this information and compare it to the minimum force required to maintain circular motion. The minimum force required to maintain circular motion will be the mass of the car times the square of its tangential speed divided by the radius of the turn it's going around. We determine this to be 3,900 newtons. Because Fs max is at least as great as its centripetal force, the car can continue to turn. If the coefficient of friction was low enough that we did not have a sufficient friction force that would equal at least the centripetal force, this car would instead just keep moving in a straight line when it attempted to take this turn. This is one of the reasons why it's very important to always slow your car as you take really any kind of turn, especially a turn in slippery weather. If your tangential speed is too great, the level of friction that's on the roadway might not be sufficient to exert a force on your car large enough to keep it in circular motion. We'll be working examples like this and others involving gravity in class tomorrow.